Okay, in this segment, this is an optional but highly recommended section of exercises. What I want you to do is, on each exercise that I write down, pause the video and try the problems. All right, so we're looking for, to save myself time writing, I just wrote, if I wrote x approaches, then that's the limit, right, as x approaches 2. But sometimes I ask you for some functional values. So let's see if I can get everything into the screen at once. There we go. So pause this and take a minute to try this exercise. So when you come back, as we approach -2, notice there's an open circle there. All right, so that tells me that my functional value as x approaches -2 does not exist. But this limit, if I stood very close to -2 and looked at these functional values, I see functional values close to 1. All right, so the limit as x approaches -2 would be 1. Now, if I were to look at -1 from the left, so that means values to the left of -1, right? So I'm walking along from values less than -1. Looking up at the function, I see functional values approaching 3. But if I walk up from the right-hand side, I see functional values. Doesn't matter that one circle's open, one circle's closed, doesn't matter. I don't actually step on -1. I see functional values that are close to 2. Now, if my left-hand limit and my right-hand limit, if these one-sided limits don't match, then I have to conclude my limit as x approaches -1 does not exist. All right, over here, as x approaches 2, again, I stand very close to 2 from the left, from the right. I actually see functional values, right? When I'm standing next to 2 but not on 2, I'm seeing functional values down here, right? Very close to -2. So this limit is equal to -2. However, the functional value is somewhere else. The functional value, if I actually step on 2, I see a functional value of 1. Now, next example that we should look at, let's do another piecewise function. All right, so here is the function that we're going to consider. F of x equals x squared for x less than 1 and 3x minus 5 for values greater than or equal to 1. And I want you to find the limit of this function as x approaches 1 from the left and the limit as x approaches 1 from the right. All right, so if you went to make a graph for this, you really don't need to make the entire graph to be able to find these limits. But if you choose to, it's good to have that visual. As I mentioned before, put 1 on your chart twice. So let's look at some values like -1, 1, 0, 1, 2, 3. So again, take a minute and pause the video and try this example. So coming back, filling in my chart, I didn't put 1 on my chart twice. Let's see here. 1, 1, right? So here I would have an open circle. Here I would have a closed circle, right? Because x does equal 1, right? And when x does equal 1, then I'm looking at this equation. So when x is 1 here, this would be -2, this would be 1, and this would be 4. So when I draw a graph of this function, I should get something looking like this. So I get this open circle here at 1. That's a parabola. And I have a closed circle down here at -2, and then the straight line. All right, so here's what my piecewise function looks like. And I can see right now by looking at it that my left-hand limit and my right-hand limit do not match. All right, so if I asked you, does the limit as x approaches 1 exist for this function, you would have to tell me, no, it doesn't, right? Because my left-hand limits and my right-hand limits do not match. So let's actually determine what our left-hand limits are. So whether you want to look at the graph or whether you want to look at your table of values, right, we can see if we walk up to 1 from the left, the functional values are approaching 1. Right, so the limit as x approaches 1 from the left is 1. And if we walk up to 1 from the right, right, and look down at these functional values, they are approaching -2. All right, so there's my left-hand limit, my right-hand limit, but the limit, right, without a one-sided direction, the limit as x approaches 1 does not exist. All right, next exercise. Let's just practice doing some examples that involve needing to factor. All right, so if I asked you find the limit as x approaches 1 of this function, and you should always try direct substitution, but it won't surprise you that I'm not going to give you a whole lot of examples where direct substitution works, right? So notice if I try plugging in 1 for x, I end up getting 0 over 0, right? That would be 1, 2 plus 1 is 3, minus 3 is 0. So anytime I have the 0 over 0 case, I should try to factor and cancel. So again, pause the video and try this example. Coming back, you should have determined that the numerator factored into 2x plus 1x minus 1. And is that right? No, I'm sorry. Hang on. There we go. And the denominator factors into x plus 1, x minus 1. So this will cancel. Then I can just plug in 1 for x, right, with direct substitution property and get 5 over 2 for that limit. All right, so next example, let's look at another case where we would have 0 over 0, but we can simplify or rewrite our expression. Let's look at one with a radical. All right, and so every time we see one of these examples with the radical, we should immediately think about using the conjugate. So again, if you'll pause the video and try this example. And coming back, the conjugate would be x squared plus 12 plus 4. So multiply that by the numerator and denominator, right? Because what I'm doing here is multiplying my expression by 1 so that I only change the appearance and not the value. And that would equal x squared plus 12, inside, outside, 0 out. So there would be last. And again, I get lazy sometimes. I don't want to write that whole denominator. But that's equal to, right, this would become x squared minus 4, which of course would simplify into x minus 2, x plus 2 over, and this does in fact cancel, right? Now I can use the direct substitution property. So plug in 2 for x, I'd get 4 over, let's see, 2 squared is 4 plus 12 is 16. So radical 16 plus 4, which is 4 plus 8, or a half, is my final answer. All right, so one more example for you to try. Let's do another complex fraction. And again, this complex fraction would be another case where if I did try direct substitution, I would get 0 over 0. And so before I have you pause the video and turn you loose to try this, let's talk about the common denominator together. All right, so here's a very ugly looking rational expression. And if it helps you, put these over 1. Right? So then if you look at the denominators, x plus 1 and x have no common factor, therefore the least common denominator is the product of these denominators. So my least common denominator would be x times x plus 1. All right, so pause the video and try it. And coming back, you should have distributed this through. Things will cancel out beautifully. So this will become x times x plus 1 plus, so as I distribute this to each part and cancel, that would be plus x over, so let's see, this part would be x squared times x plus 1 minus 4 times x plus 1. And I know how tempting it is. You know, there's some ugly algebra here. I know how tempting it is to just say, oh, can I cancel these? Right? But remember, you can't cancel from a sum. Right? You can't cancel out of one term without also canceling from the other term. All right, so if I wanted to divide each term by x plus 1, I could do that, but see, then this doesn't have an x plus 1. So my best bet here is to actually distribute everything and then try factoring. Although let me distribute here in the numerator, so I would get x squared plus x plus x. Let me do this in the denominator. Notice how each of these has the factor x plus 1. If I factored out an x plus 1, right, then I would be left with, from here I would be left with x squared, and from this term I would be left with minus 4. All right, so that was an easy way to handle the denominator. And up here I've got x squared plus 2x. All right, so now let me factor that as much as I can. So limit as x approaches -2. That's x times x plus 2 over x plus 1 times x plus 2 times x minus 2. These would cancel, right? And now I'm ready to plug in -2 for x. Once I plug in -2 for x, now that I've canceled that problematic 0 over 0 factor, I can plug in, and I will not get 0 over 0. I will, in fact, get a value for the limit. So this problem definitely had some more challenging algebra to it. So this would be negative 2 over negative 1 times negative 4, or negative 1/2. And I'm just looking up here to check my work for a minute, but I think it's good. All right, so this concludes the extra practice segment. So thank you for participating.